My name is Eli Huerta. I am the director of the Center for AI Innovation. And today I'm very glad to introduce Bryan Clark. Bryan is an associate professor in the Department of Physics at the University of Illinois. He received his PhD at University of Illinois, so he knows the university very well. Then he was a postdoc at Microsoft Research. Then he moved to the Kavli Institute for Theoretical Physics in Santa Barbara. And then he moved to the Princeton Center for Theoretical Studies. Bryan is working in areas of computational condensed matter and quantum computing, where he develops and applies computational methods in these areas. And his interests in machine learning focus on developing novel approaches to use deep learning to represent quantum wave functions. And he is well known for pioneering an inverse approach to finding condensed matter models and then applying machine learning to analyze experiments. So this all sounds quite exciting. Please, Bryan, take it away.
Awesome, thanks. Welcome again. So just to give you a little bit of context, I'm in the Department of Physics, and I work in the areas of condensed matter, which is essentially the study of everything around us, materials, etc., as well as in the area of quantum computing. One of the main themes of my research group over the last couple of years has been the both the utilization as well as the development of new methodologies in machine learning to study physics, study quantum computing, study quantum materials, etc. And so this is just sort of an eagle-eye overview of some of the machine learning work we've done in the last couple of years. And my goal today is sort of twofold. I'm going to talk in a reasonable amount of detail about two particular projects looking at quantum ground states of fermions, those that have sort of complicated sign structures, and simulating quantum circuits. But in addition to that, I'm actually going to spend a fair amount of my time just sort of highlighting kind of one slide each at sort of a point in the talk where sort of we have the background to talk about it, some of these various other machine learning things we've been doing, just to give you a flavor for what we're interested in. So there won't be a lot of details, but it'll just kind of be kind of a one-slide narrative of the sort of things that we are interested in tackling. All right, let's go ahead and get started with that. So the first thing I'd like to talk about, this won't be sort of a main thing, but just kind of a one-slide narrative in looking at Majoranas in superconductors. So just to give you a little bit of background, if you want to build yourself a topological quantum computer, which would be nice, they would be error robust. Sort of the best path forward is you take some nanowires, some superconducting nanowires, and you layer it on the appropriate material. And at the end of these nanowires, there are these particles that are essentially called Majoranas. And the name of the game is that you need to take the Majoranas and you need to drag them around. Essentially, at the end of the day, you want to braid them. You want to have them pass by each other. And so the key sort of technological question here is, how do I move around the Majoranas? And if you have all the time in the world, there's sort of a standard, well-recognized approach for moving around Majoranas. This purple is a Majorana. And if you have all the time in the world, you should just move it very, very slowly. If you move it very, very slowly, the fidelity of the Majoranas are very good. Nothing breaks down. There are no errors. Unfortunately, in the real world, so I'm a theorist, I don't have to deal with the real world, but experimentalists who have to deal with the real world, if you move Majoranas very, very slowly, all sorts of bad things happen in the interim. There's quasi-particle poisoning. There are all sorts of errors that show up that break your quantum computation. And so instead, what we need is sort of smart protocols to go ahead and move the Majoranas from sort of point A to point B reasonably quickly. So there is where machine learning can come in. So for a long time, there is a large class of protocols called bang-bang protocols. And these protocols, the community had largely converged on as sort of the best way to move around Majoranas if you're going to move them quickly. And so what we did is we said, look, we can write this down as sort of a machine learning problem, kind of a reinforcement learning game. We can say, look, you need to get your Majoranas from point A to point B, and you have a certain amount of time. And you can change essentially the potential. You can drag them around. And so one of the really cool parts about this project is we sort of sat there, set up this machinery, told it to go, and we get results like this. They're really noisy. All of this jiggle shouldn't really be there. But what we see is qualitatively, you start somewhere, you jump, you linearly move for a while, and then sometimes at the end, you jump again. So this one is the cleanest, you jump, you sort of move linearly, and you jump again. And what this did is this sort of inspired us to come on with sort of a brand new qualitative class of protocols for moving around Majoranas. And so one of the things that I like about this project is that in some sense, this was really a nice synergy between machines learning things and us figuring out how to analytically understand things in a qualitatively new way. And so this gave us sort of a whole new qualitative class of protocols for pushing around Majoranas. That sort of was much better, or I don't know if it was much better, but it's better than the standard state of the art that existed in the community. And so that's just sort of a nice example where a little bit of machine learning can sort of really push things forward in a long way. So another project that we've been doing a lot of work on is identifying defects in STEM images. I should say this Majorana project is with my student Dee, as well as collaboration with Graham Kell and his student Luke, as well as Juan Corrasquali. This identifying defects project is with a number of people here, some of my students, Pinchane and her group, Nihil, as well as Andre Schleffly. And so there, we had sort of a different problem. The game was the following. So Pinchane is an experimentalist down the hall in MRL, and she does scanning transmission electron microscopy. And she takes beautiful images of 2D atomic layers. So on the left is sort of a raw image of a 2D atomic layer. And in this, there are all sorts of defects and vacancies and things. And the typical approach to dealing with defects and vacancies and things is you hire a lot of graduate students and they go through 1 million atoms one by one and they circle the defects. So they circle the vacancies and things. And so this is sort of an approach that's right for the application of machine learning. You really would like some automated way of doing this. And so we worked in collaboration to really develop sort of a machine learning workflow to take images like this and automatically identify where the defects are, double vacancies, single vacancies, interstitials, et cetera. And one of the sort of most difficult things actually in this project was we had labeled data from simulations, but the neural networks actually were pretty good at distinguishing between the simulations and experiments, which is not what you want. And so we had to spend a lot of time figuring out how we could update our simulations in such a way that they had enough CRUD on top of them that the neural network really didn't know the difference. Okay, so those are two sort of high-level vignettes about just kind of the flavor of things we're doing. One thing that I want to spend a lot of time talking about is this work on quantum ground states. So quantum ground states, just in general, is the following. So the world around us, we have lots of materials. Those materials have electrons in it. And the electrons and materials are effectively at zero temperature for all intents and purposes. And so if you want to understand a property of a material, then really what you want to do is you want to get the ground state of that quantum system. And I'll tell you kind of mathematically what that means in a minute. But that's the game. And then once you have your hands on the ground state, then you can go ahead and you can measure properties. You can calculate various different things. So this is really what we mean when we say, we want to go ahead and simulate materials. And so we've been doing various work on quantum ground states. And I will tell you in detail about one of those works. This is figuring out how to build quantum ground states for fermionic wave functions. Okay, so let me just back up for a minute and give you kind of the mathematical structure of what's going on. So a quantum problem, sort of the rules of the quantum problem, the model that you're starting with is defined by a Hamiltonian. That Hamiltonian is just a big matrix. So a very reasonable sort of thing is you have this big sparse 4 to the 200 by 4 to the 200 matrix. And that's your starting point. That's the model that the universe hands you. And there are various different models that are relevant for different materials and different physical systems. And then the game is that you want the lowest eigenenergy of this sparse matrix. And essentially, you want to compute properties of the lowest eigenvector. So functions of this lowest eigenvector. Okay, and the tricky thing, sort of in some sense, the only fundamental tricky thing, is this vector is a 4 to the 200 vector. So storing it explicitly, storing this quantum state, will require more bits than there are atoms in the universe. And so as long as you're sort of up to only 20 spins or 20 electrons, then this is a practical approach. You just write down the matrix, you use Lanczos, you diagonalize it. And we do this because in many cases, we want exact answers. But once you get up to sort of 200 electrons, and that's not so big, life has to change. You really need to come up with an alternate approach. And so one common approach in the community is to say, look, can't write down this big thing. We have to find some way of compressing it. And where we're going to be going is asking, how can we compress it using sort of a deep learning kind of architecture? And we'll fill in those details as we go on. So we can think of this large vector really not as a vector, but as some map from some index or some binary number or some configuration to a complex number. So it might say, look, this is index 13, 1101, corresponds to spin up, spin up, spin down, spin up, or if we're working with electrons, electron there, electron there, electron not there, electron there. And you have some map for that particular configuration, the number is 0.03. And so for some other configuration, it might be something different. And so you have some black box. In each configurations, it spits out a number. And now the name of the game is to figure out how you can efficiently and compactly represent this black box. Can you see where my mouse is when I'm pointing to things, by the way?
Yes.
Yes. So the game here is to sort of figure out how is it we're going to compactly and efficiently represent this black box. So in practice, really, you don't guess a single black box. What you do is you guess sort of a whole manifold of wave functions that are parameterized by some set of parameters. So you say, look, I have lots of possible functions. I might possibly be a good guess for this ground state eigenvector, for this 4 to the 200 vector that I'm trying to get my hands on. And then what we typically do in the community is we write down some objective function that says, how good is this guess? And the canonical objective function is the energy. So the energy depends in some way on this set of parameters that specify the function in my black box. And there's some formula to compute them. What you do is you sample from these various configurations. You sample the probability of a given configuration, and you do that by Markov chain Monte Carlo. And then you just generate sort of the appropriate averages to get the energy. You generate the appropriate averages to get the gradients. And to zeroth order, you sort of do stochastic gradient descent. Step downhill with respect to the energy, with respect to these parameters, and try to find which wave function within this manifold is actually a best guess, best approximation for your vector. And so now there are two questions. How do you do that optimization actually? And what is the class of wave functions that you're going to consider? So just to sort of, again, another 2-minute aside, let me stop and just discuss how to do this optimization, because it's something that is both interesting and we ended up working for a couple of years trying to improve upon the current state of the art, being inspired by kind of a supervised learning approach. So what would you do if you thought, this is some sort of neural network kind of thing, some sort of machine learning kind of thing? Well, what you would do is you would do some sort of stochastic gradient descent. And people working in quantum Monte Carlo used to also do that. And that works all right, but there are lots of problems doing kind of a stochastic gradient descent. So it turns out that for these particular applications, the convergence was extremely slow. And so over the years, the community came up with better approaches. And these approaches are superior. They're sort of generalizations of natural gradients that improve upon natural gradient before natural gradients existed in the machine learning community. There's sort of different things you can do. But the obstacle was all of these new and improved things scale very badly with the parameters. So the number of steps you have to take, the number of iterations you have to take to converge is much smaller, but the scaling with parameters are sort of p squared, p cubed, where p is the number of parameters. And this is undesirable because if you want to work with 10,000 parameters or 100,000 parameters, things get really slow fast. So we spent a few years thinking about how to get around this. And what we came up with is we came up with an approach that was sort of inspired by supervised learning. So I'm going to give you kind of half a slide on this and just to give you a sense for what we were doing there. So how does supervised learning work? Well, the way supervised learning works generically is you say, look, I'm going to give some supervised learning algorithm a bunch of images, say of cats and dogs, a bunch of labels, they're cats and dogs. And then at the end of the day, it should learn the difference between a cat and a dog. I'll hand it a new image and it should know. So we're going to do something a little bit different. Instead of an image of a cat, we'll give it an image of a configuration, spin up, up, down, up. And instead of the label cat, we'll give it sort of the label that corresponds to the amplitude of the quantum vector that we wanted to get out. And so that has amplitude 0.005, and down, 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 up has amplitude minus 0.0035. And then what we'll do is we'll ask the supervised learning algorithm to sort of learn this improved wave function. Okay, there's a long backstory about how we get our hands on these labels for this improved wave function. I don't want to tell that story at the moment. It's sort of a little bit tangential, but they're sort of quasi-standard ways of doing this. And okay, we don't improve them for this particular context, but there's nothing particularly deep there. And so we end up in a situation where we do this for a step, and then we kind of iterate on it. We got to a slightly better wave function, and then we do the supervised learning again. We get to a slightly better wave function, we do the supervised learning again, et cetera, until we get down to a kind of high quality result. And so this ends up being linear in the number of parameters, but essentially giving you the convergence rate that you would get if you use some of these more sophisticated methods. And so this was sort of a win-win all around. And it really was sort of inspired by thinking through ideas about supervised learning. Okay, so that's one game. You got to figure out how to optimize these things. But the second game is if you know how to do the optimization, you still have to pick what lives in your black box. What is your class of wave functions? What is your compactification of this huge 4 to the 200 vector? Okay, and so there are standard things and there are sort of new things. So let me start with the standard things. And I give this not only just as an exemplar of the kind of thing we're doing, but, or the kind of thing that's been done forever actually, but it actually sort of, this character will play an important role in our new and improved techniques in a minute. So the generic Hamiltonian, if you really have a bunch of electrons and they're repelling each other, et cetera, has a complicated wave function. The exact wave function really is something that is not compressible. But there are simple Hamiltonians, and simple Hamiltonians, kindly enough, are already sort of highly compressible. So one Hamiltonian of that form is the following. Doesn't matter what this is. The physics of it is as a non-interacting fermion. Typically you have electrons, they repel each other, right? They're both negatively charged. Here, they don't really repel each other other than through the Pauli principle. Two electrons can't be in the same spot, but that's the only way they see each other. And this problem is simple. Physicists have been able to solve this problem for 100 years. And the amount of information that you need to sort of encode the wave function for this problem, this ground state eigenvector, is small. So if we consider a 4-site 3-electron problem, what we do is we can solve for a set of single particle orbitals. So this is just 12 numbers. There's an algorithm to generate these 12 numbers, but for all intents and purposes, there are 1, 2, 3 for the 3 electrons, each on 4 sites, 12 numbers that you have to work with. And then what you do is you say, oh, what is the configuration for electron, no electron, electron, electron? You mask against this, these 12 numbers, this 4x3 matrix. That gives you a 3x3 matrix, because this one is irrelevant, the electron is not here. And then you take the determinant of it. This is called a non-interacting Slater determinant. You can proceed to dress this determinant in various ways, adding various correlations on top of it. But the key thing is this gives you a great physical starting point. It's very small. If I have a 200 electron problem on 400 sites, I only need 200 times 400 numbers. And I can use these numbers as a parameter. So I go and I say, look, I have 12 numbers and I have to just optimize for those 12 numbers. Or I have 400 times 200 numbers, I have to optimize for those numbers, no problem. This has all the right physics because you start with sort of a Hamiltonian that is reasonable. So it has sort of the right anti-symmetry, the signs change in the right way when you swap electrons, etc. So this is all well and good, but just not accurate enough, even when you dress it in various ways. Something that has kind of been pioneered in the sort of last 3 or 4 years, and somehow I lost the citation to this, but this is originally pioneered by Giuseppe Carlio and Matthias Troyer and company, although in the context of restricted Boltzmann machines and not feed-forward neural networks, is to do the following. You say, look, it's just a black box, right? We're sort of a machine learning community here. The most natural thing to do if you want to build a black box is to stick some sort of neural architecture there. So here's the game. You have a configuration, electron, no electron, 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 map it to some binary number. And then you just feed it through some feed-forward neural network. And at the end, it spits out some number. You say, great, that is the sort of compression. I have some deep neural architecture. That is the compression of my wave function. And it turns out that this works reasonably, but really breaks down for electronic systems with fermions. And electronic systems are the systems that we primarily care about. All materials around us are full of electrons. It's a little bit unfortunate if you have a scheme that doesn't work great for electronic systems. And what I mean by doesn't work great is actually you get pretty good results. But those results on average don't seem to be regularly beating kind of the old standard start with the physics and optimize things that we've known and loved for a while. And I can sort of motivate in a couple different ways why this is hard. So one way this is hard is, let's imagine that you wanted to solve the simplest problem, right? We already worked on the simplest problem. The electrons don't see each other at all. That answer is a determinant. If you want to get a determinant optimized out of a feed-forward neural net, it's a pain in the neck. I don't know if you've ever sat down and tried to optimize a feed-forward neural net to match a determinant, but it doesn't work particularly easily. And in general, one motivation for why these things are difficult is because you have a lot of sign structure running around. So what that means is that the function, this very high dimensional function that you're trying to learn, is highly oscillatory. And it's highly oscillatory just as a practical matter. It makes these architectures work worse. Of course, as a principle, right? There's a theorem. If I use a gazillion neurons, it will work. But if I want to try to represent it with a small number of neurons, things are not great. Another way to see why this is sort of a potentially difficult problem is if you have something that's all positive, a probability distribution or something like that, there are lots of neural architectures that you might consider using. Transformers, restricted Boltzmann machines, etc. If I have something where I have plus and negative signs or maybe complex numbers, life gets much worse. Lots of the neural architectures, at least naively, are not usable, although people have tried sort of, with some limited success, adding sort of complex weights into things like restricted Boltzmann machines. Okay, one last thing I'll say. One thing that would be nice that we don't know how to do that would partially solve this problem is if we knew how to enforce anti-symmetry into our neural networks. So one of the things that we've been working on that I won't tell you a lot about is figuring out how to enforce the symmetry of sort of physical problems into deep learning architectures. So I give you a neural network and I tell you, my physical system is translationally invariant or rotationally invariant, or you need to be anti-symmetric. Every time you swap two inputs of the neural network, it better give you exactly the same magnitude out as your number, but a different sign. And this sort of thing is hard to encode. And if we knew how to encode it better, we would be able to solve this problem better. Okay, but in lieu of that, we've developed sort of an alternative approach that we think is sort of a nice, elegant way to get around this problem. So really, I've shown you two approaches. One is really sort of a black box, close your eyes, throw a neural network at it. And one is sort of a more physics-inspired approach. You can solve the simple problem, you get a determinant out, and then you address the determinant. And now what we want to do is we want to combine these two ideas. So here's what we're going to do. We have our neural network again, but we're not going to spit out the answer. We're not going to spit out the complex number that corresponds to the element in our eigenvector. Instead, what we're going to do is we're going to generate a set of single particle orbitals. So this is really a configuration-dependent set of single particle orbitals. So before, you had one set, 12 numbers, and for every configuration, you masked against those 12 numbers. Now, life is different. For every configuration, you have a new set of 12 numbers. And those new set of 12 numbers is generated via a neural network. So this is not, this sort of configuration-dependent single particle orbitals is not without precedent. So there's a concept called backflow in quantum wave functions that is very similar in spirit. And so a lot of the novelty here is really figuring out how to combine this with ideas from machine learning. And so you end up generating a new set of single particle orbitals. The single particle orbitals, you go ahead and mask against. You mask against, you get a 3x3 matrix. You take the determinant. That determinant gives you the amplitude. Okay, so this is a new wave function or class of wave functions that we've developed. You now have a different set of parameters. You're not tuning these 12 numbers. What you're tuning is you're tuning all of the weights and biases in this neural network. And right, that is the thing that you were optimizing over. And so now we can step back and we can ask, given this particular class of wave functions, how well can we do? So let me guide you through that. So this is percent error. So if you do the standard thing, that's what SO is, sort of the standard, we know and loved Dress-Slater determinant that we've been doing forever. You kind of have a 5% error. This is on a Hubbard model, for those of you who know what that is. This is sort of the standard benchmark in the community. This is sort of the hard point. If we really knew how to model and understand this system well enough, at least sort of variants of this system, we could understand superconductivity and lots of other exotic physics that we don't really have our hands on at the moment. So we get something like 5% errors using the standard approach. And now what we can do is turn on our new method. And what our new method does is we can put as many neurons as we'd like. So if we have n/4 neurons, so a quarter of the neurons as the size of the input, we get down to kind of 3%. That's a pretty good step. And if we go up to 4n neurons, we get down to a quarter of a percent. So we really improve things, not a quarter of a percent, 1.5%, sorry. And then we use sort of the standard extrapolation in the field, we're down to 0.5%. So this is pretty good. We got an order of magnitude improvement. We went from 5% to 0.5%. These are two different methodologies. These are two different sort of physics-inspired mean fields. It's not important what these two different lines are. Okay, so that's great. We got an order of magnitude improvement using sort of 4n neurons. That's a really good start. Not only do we get better energies, which is sort of our objective function, that's good. We also get the physics better, the qualitative physics better. So one thing that physicists are obsessed with are symmetries. And we discover that, kind of surprisingly to us, that by using this technique, we restore the symmetries. So what am I showing you here? This here is the single particle orbitals. And what I haven't told you yet is there's actually a set of single particle orbitals for the up single particle orbitals and the down single particle orbitals. This is this 3x4 matrix, but there are two of them. You have up electrons and down electrons. And this is a heat map of the single particle orbitals. This is using the standard Slater-Jastrow, been used for 50 years approach. And what we know from the physics is we know the up orbitals and the down orbitals should be the same. But if we look at this, and you just look at the heat map, the up orbitals and the down orbitals are not the same. And that's because it was better with respect to our objective function to break this symmetry, even though we know in the exact wave function the symmetry ought to be there. But now we can go take our new approach, the neural network backflow approach, which is on this right side. And we can't ask for the single particle orbitals because there's a new set depending on the configuration. We take a prototypical configuration, it's this one. We look at the heat map of the single particle orbitals, and what you'll notice is that they're much, much closer. Essentially, the symmetry that the up and down should really be the same has been restored. And so that's really sort of a qualitative aspect that by combining this machine learning with sort of physics-inspired approaches, we really got an improvement both in the objective function, both in the energy and in the physics. We also changed the sign significantly. That was important for technical reasons. We've tried to sort of open the black box. We weren't very successful in opening the black box. So we stared at our neural networks and we said, what are they doing? We learned only one thing, but let me tell you the one thing we learned. So there's really a spin-up neural network and a spin-down neural network. There are spin-up electrons and spin-down electrons. The spin-down neural network really wants to know where the spin-up electrons are. The spin-up neural network really wants to know where the spin-down electrons are. All right, that's not surprising, but it's the only thing we succeeded in learning by trying to stare at our black box and say, what physics, what is it sneakily encoding that we didn't know about before? I don't like to put tables in talks, but the thing to take away from here is we've done sort of a suite of the difficult problems in physics, Hubbard models, various forms, and sort of the difficult optimal doping regime, Kagame models, spin liquids, et cetera. And our errors are kind of at the level of between sort of 2% and 0.2%. So this is really good. It's not amazing. We'd like to do a lot better. You can ask, what is the obstacle to doing a lot better? Well, it's really just computer time at this point, as best I can tell. This is slow. It scales as n to the 4. So if you want to do 200 electrons, it's 200 to the 4. That's a factor of 200 more than the standard approaches. And so it parallelizes extremely well. All a variational Monte Carlo does. But nonetheless, a factor of 200 is a big deal. And so until we have sort of bigger machines, or until sort of the code and the machinery is really working on multiple GPUs, we have sort of prototypes working on one GPU, but not many GPUs at once, this is really in some sense our major bottleneck. Okay, so that's what I wanted to tell you really about that one project. Let me just pause for a minute and give you a vignette about another quantum ground state project that we've made progress on and we're excited about. And this is thinking about wave functions for infinitely sized systems. So you may have noticed so far, everything I've told you, we have a situation where we have to work really hard to get the physics out. And we have to work really hard because there's this really difficult optimization problem. And we have to work really hard because, we meaning in some sense the computer, the scaling is not amazing. So the algorithms I just showed you scale as n to the 4. So, I mean, there are 10 to the 23 electrons in a sort of standard chunk of material. So we're never going to get anywhere near that. But even if you want to go to sort of 1,000 electrons or 10,000 electrons or something, this is sort of way beyond what we can do. We can maybe do 100 electrons or something. And so let me not say 1,000 or 10,000 is way beyond what we can do. We can do that, but it's a lot of work. We need huge machines, et cetera. If you wanted to go an order of magnitude above that, life would be very difficult. So one approach that one could hope to be able to do is to somehow learn your wave function on small systems and have it generalized to larger systems. And that would solve, that would overcome a lot of the problems that we have. Okay. And so here we've done a very tiny baby step to that, a very tiny example. So this is the simplest physical system we could write down. It's in 1 dimensions, it's a Heisenberg model, it's extremely simple. But nonetheless, we succeeded in sort of doing this dream to some extent, where we trained it on a very small system. And we said, look, does this training on a small system work for other systems? And so we can ask, what did we train? Well, you might think, you want something to kind of generalize to bigger systems. Maybe you want to use some sort of convolution neural network sort of thing. And so that's what we did. We had a wave function inspired by convolution neural networks. We trained it on 40 site. This is our training energy. This blue dotted line is the exact energy. And then we just asked for the same parameters sort of generalized in the right way. How well does it work on 10 sites? So this is the 10 site energy using the same parameters, and this dotted line is the exact energy. This is the 20 site using the same parameters. This dotted line is the exact energy. 30 site, all the way out to sort of hundreds of sites. This is the exact energy for the infinite system. So it's decent. This is like a really great start. Somehow we really have a system where we can kind of train some morally inspired convolution neural network wave function. We get it right for one energy, and it works pretty well for all different system sizes. We don't know how to successfully do this for more complicated wave functions, for more complicated structures at the moment, although it is something we're thinking about and working on. And this, I think, is sort of a cool and important next step in the field to figure out really how we can avoid working for sort of large systems. Okay, that was just my one slide vignette there. I want to give you sort of in the intermission here another one slide vignette. So we've really been pushing forward on the use of inverse problems in the field of computational condensed matter. So everything I've told you so far, my whole sort of last story, etc., the game is the following. I gave you this huge matrix. It tells you the model of your system. It tells you the rules of the system. And then your goal was to get this ground state eigenvector. And then once you have the ground state eigenvector, there are all sorts of properties that you can compute from it. Okay, and then if you want to do this, if you're interested in some interesting physics, you're interested in the physics of spin liquids, what happens is you guess some Hamiltonians and you sort of throw darts in the dark. And you say, maybe this Hamiltonian will give me this cool exotic physics that I care about. And so, for example, the search for spin liquids spanned 30 years. Phil Anderson wrote down a guess for a Hamiltonian that might give a spin liquid 30 years ago. It turned out it didn't give a spin liquid. Ever since then, there's been sort of this attempt at finding new spin liquid Hamiltonians. And as a community at this point, we're maybe up to half a dozen or something. And that's good. And it's a huge amount of work to try to find Hamiltonians that give these spin liquid wave functions, because for every single one of them, you've got to do sort of a lot of numerics, a lot of computation, many papers on each Hamiltonian, arguments back and forth in the community for what gives this kind of thing. And so he said, look, we really want to kind of invert this process. If we have some target in mind, if we have some property that we want, what we should do is we should start with the wave function, or we should start with the symmetry property that we want to start with, and then we should do the inverse method. We should just turn the crank somehow, figure out how to get our machine to generate the set of Hamiltonians. Okay. Let me give you sort of 1 minute on kind of what one needs to do this. So we have various inverse things. Here I'll tell you the inverse thing for starting with a wave function. You start with a wave function you want. Maybe it's written as a matrix product state or something you can do variational Monte Carlo on, or maybe it's something that you have sitting in your quantum computer. And then you go measure certain properties of that wave function. If it's sitting in your quantum computer, you almost literally do sort of the measurement in your quantum computer. If it's sitting on your classical computer, then you do Monte Carlo and you measure it. You measure some set of properties, and the set of properties that you have to measure builds you what we've sort of called the quantum covariance matrix. So quantum covariance matrix is called that way because it's really sort of the quantum generalizations for the standard statistical covariance matrix that you know and love. I'm not going to explain this formula, but it looks like something that might look like a covariance matrix. And once you have this covariance matrix, it's a pretty small matrix, maybe it's 1,000 by 1,000 or something. And then what you do is you diagonalize it and you look for the null singular values. And every null singular value corresponds to an eigenvector or a null singular vector that gives you one of these Hamiltonians. And so we use this approach, or sort of a similar approach with symmetries, to find sort of a whole family of new spin liquids that people didn't know about. So this was really sort of a nice way to target the physics that you really care about. And so we've really been sort of pushing this both methodologically as well as sort of then applying these inverse methods to solve various sort of targeted problems that we want. Okay, great. And so now for the last 10 minutes, what I'd like to tell you is sort of another involved story on work we're doing simulating quantum circuits. So this is a quantum circuit. It's what a quantum computer will run. You have some input, which is the quantum state. You have a bunch of gates. These are whatever, Hadamard gates, swap gates, T gates, whatever. And again, similar to the story that I told you earlier, the quantum state, if you were to write it down sort of inside your computer explicitly, is of size 2 to the n, where n is the number of wires. Here is 16, but if you want to emulate Google's machine, which has 53 wires, you need a 2 to the 53 vector. If you want to emulate tomorrow's machine, which has 100 wires or 200 wires, you need a 2 to the 200 vector. And so pretty quick, you run out of atoms in the universe. So what is let's say you want to benchmark this. Let's say you want to simulate it. Well, at some point, you just run out of steam, right? That's why quantum computers are good, because we can't always simulate it on our big machines. But at some point, it's important to be able to simulate it as far as you can go for benchmarking, for showing that you really have a quantum advantage, for testing out and developing new algorithms. And the naive approach is, look, you just store this state. You store all 2 to the 50 numbers. and you update the exponentially large vector after each gate application. And I say naive, but it's kind of a state-of-the-art approach, actually. So my undergraduates code this in their class, and they can simulate 20 qubits. The IBM sort of coded up in a very sophisticated version of this and claims that using this approach, you could simulate Google's 53 qubits. So this is really sort of assuming you had access to Summit or something. So this is really one of the top current approaches. And the second approach that exists is sort of using tensor networks. And tensor networks are great, but really sort of break down in 2 dimensions. There's a lot of great ongoing work to make that better, but we really need some new paradigms here. And so that's what we've been developing. We've really been developing sort of a new paradigm, a new approach to simulating quantum circuits. And so the game there is the following. So what we do is we do sort of a mapping, a dictionary between quantum states and honest to goodness probability distributions. So the story I told you before is one of the difficulties that made it difficult to use various sort of neural architectures is that we were working with positive and negative things and not probabilities. And so now we are using an approach. This approach is known in the quantum information sort of literature, although has not been heavily used in sort of a numerical way like I'm about to tell you. And then once we have our hands on a probability distribution, we should be able to use any generative model to represent it. So we're going to actually sort of compactify this probability distribution that stores the state of our quantum computer with an autoregressive model. Okay, so quantum state to autoregressive model. So now quantum gates are actually going to go to quasi-stochastic matrices. So a quasi-stochastic matrix is a matrix that you multiply by a probability distribution and gives you a probability distribution back. It's rows sum to 1, and but it has negative numbers running around in it. So that makes life a little bit difficult for other approaches. And then what we need and what we've developed is some algorithm that takes a circuit and updates the autoregressive model after each gate. This is the eagle-eye view of what we're doing. So we simulate the circuit by the quantum state as a transformer. After each gate, we have a way to update the transformer. Now I'm going to tell you some details. The details are cool, but if you just want to know, look, what's the high-level picture of what you're doing, this is what it is. Okay, so how do we go from the quantum state to the probability distribution? So for the experts in the audience, this is the quantum information experts in the audience. This is using the POVM basis, using a set of projector operator value measurements. If you like tensor network diagrams, this is the tensor network diagram that we're using. If this doesn't make sense, that's okay. You can just say, look, I have a wave function. I have some set of matrices that are morally speaking measurements, and a function of those matrices and the wave functions gives me this probability distribution. This is a probability distribution over 4 to the n things. These a's go from 0 to 3. This is a bit 4 number, so not bit 4, but like a not binary. It's quartary or something. So this is a number in base 4. And so I have 4 to the n different probabilities. These 4 to the n different probabilities then get compacted into being represented by a transformer. Okay, so the quantum state goes to this 4 to the n probabilities. Then we stick it in a transformer. This is the computational graph of a transformer, particularly the transformer that we use. There are a couple features of the transformer that are advantageous for us. So let me just walk you through those. So one feature of the transformer is you don't need to use Markov chain Monte Carlo to sample it. You can sample a transformer exactly. And roughly the way that works is that after you choose sort of the first 4-bit correctly, then the next 4-bit is conditioned on the value of the first 4-bit. The next 4-bit is conditioned on the value of the last 2 4-bits. And so you can just sequentially build up your configuration. So you can sample this without Markov chain Monte Carlo. I'll tell you why that's useful in a minute. There's no autocorrelation time. The other sort of major feature of a transformer that is useful for us is you can hand it a configuration, 0, 3, 1, 1, 3, 0, and it will tell you the probability of that configuration. And that is the other sort of feature that we need from this transformer. Okay, now you got to take the quantum gate. You can't apply a quantum gate to a transformer. Instead, you can't apply a quantum gate to a probability distribution. So instead, the quantum gate gets mapped to some quasi-stochastic matrix. That quasi-stochastic matrix is sparse. Again, if you're an expert in quantum information, this is the right formula with the MPOVM bases. this is the tensor network diagram that gives it to you. If you're not, it doesn't matter. Quantum gate goes to sparse matrix. Okay, now we need an algorithm, right? Before you had a quantum state, gates got applied to it. Now you have a probability distribution, quasi-stochastic matrices get applied to it. So what we're going to do is we're going to use as our objective function, essentially the KL divergence between where we want to go and where we are. So let me outline this a little bit more carefully. And so here is sort of a cartoon. This is the state that your transformer is at. This is the state of your quantum computation. And if you could apply the gate exactly, you would go here. And what we like is we'd like to get a new transformer that gives us as close as possible to that exact application. So this is an exact application to our current approximate state. This would be the exact quantum computation if we could follow it. Okay, so our objective function is the KL divergence between the exact state and as best we can make the transformer go. Sorry. So what should we do? We should write down a gradient of the KL divergence. There's some formula here, and now we need to compute the formula. We'll compute the formula by Monte Carlo. So what we do is we sample the A's. We sample the A's from the current probability distribution of the transformer. We ask the transformer, what is the value here? We compute this exactly. This can be computed exactly because it's a quasi-stochastic matrix and it's sparse. So we can just sum over all A prime that is connected to A. We compute this gradient by automatic differentiation, and we essentially step downhill by stochastic gradient descent. One cute thing about this is actually, if you just worked out the algebra, this is not the formula you would get. We've actually added some additional terms to this formula. We've essentially added some things whose means are 0, but nonetheless reduced the variance. So we've done some sort of cute variance reduction techniques to make this much more efficient. Okay, so I know I'm about out of time. I just have one more slide. So this is our algorithm. Given a transformer, sample the transformer, sample from the transformer to minimize the KL divergence between where you want to go and where you actually go. So how do we do? Well, there are various metrics that you can use to ask what the quality of this is. Our metric here is sort of the classical fidelity. We have some probability distribution we wanted to get to. That would be following the exact state. And we have some spot that we actually got to. And we can ask how well. So we can do various things. We can take some simple circuits and crank up the system size. Circuits here are simple because we know what the right answer is analytically. And so if we go up to kind of 60 qubits, this is sort of really, really big, right? This is bigger than you can store in a single vector. Our classical fidelity is sort of 90%. This is good, it's not amazing. It's better depending on what simple circuits we do. And we would like to do better, but this is a really sort of impressive first start. We can do the opposite. We can take a really small system, which we can just solve exactly, but a hard problem. So this is a variational quantum eigensolver circuit. This is the kind of thing you would run actually on a quantum computer to simulate molecules on a quantum computer. And there, for these very tiny systems, we get kind of 99% accuracy. Again, this is great. This is a really good start. It's really new paradigm for simulating quantum circuits. But there's still a long way to go to sort of optimize and fine tune and make this optimal. Okay, great. So let me just thank the people who actually did the work. So this is my group. The people in red boxes are those who are actually on the papers that I talked about today. Always thank the funding agencies who had funding from the Department of Energy. My various other sort of collaborators outside of my group are here. And so then I just like to sort of summarize with this and thank everyone for talking and watching, and I'm happy to take questions.
Thanks a lot, Brian. Let's give a hand to the speaker. All right. So do you have any questions? Anyone, you can just go ahead, unmute yourself and ask your question. Okay, while you think about this, I have a question for you, Brian.
Yep.
So if you were to sell this work to a person that is not knowledgeable of AI or quantum physics, and they ask you, what is the key contribution that machine learning has brought into quantum physics that was not possible before with traditional approaches, what would be that elevator pitch?
Yeah, great. So I think the real thing is the ability to represent so let me say two things because there's really sort of two classes. As for the main thing that I talked about, these quantum ground states and the quantum computation, the main benefit is that there are these very general ways to represent very complicated high dimensional structures. And so in some sense, this is like one of the most complicated like data science problems of all time. You have this extremely complicated high dimensional wave function, and you need to somehow accurately represent that. And a lot of these deep learning architectures are very powerful in accurately representing that. Although I think we saw that there are sort of obstacles that are fundamental to physics related to things not being probability distributions and having a lot of negative numbers, relating to symmetries that still really need to be overcome in order for us to sort of really fulfill this vision. So I would say that that's one class, the ability to represent this high dimensional wave function. The other class is really sort of more related to sort of experimental things. How do you push around Majoranas? How do you image defects? And there, I think the big thing that it has brought a way to automate something that used to take many, many graduate student years worth of time. And so the real trick is that by using these ideas from machine learning, you can replace humans in part of the loop, and that allows humans to really tackle sort of higher level problems than sitting there and circling where all the defects are, or by hand trying a bunch of different protocols. So that's what I would say.
All right, another question from everyone. Very quiet audience today. So let me ask you another question. This is something that I noticed in your list of collaborators.
Mm-hmm.
It seems that you have some machine learning experts in your team. Has it been easy to establish this type of connections with people that have no background in physics? How do you engage a CS expert so that you can also contribute something into machine learning?
Yeah, that's a great question. Right, so we have various, lots of great collaborators around, and some of them certainly are experts more in machine learning related things. And, you know, I think actually you might have sort of naively thought that it would be difficult, but I actually think there isn't too much of an impedance mismatch. I mean, so of course there's a little bit because there's a lot of jargon and terminology and sort of background in physics, but I think there are a lot of places where it takes some time, but you really can start to kind of abstract away the particular kind of mathematical questions that you're after. Once you begin to get to that point, that's sort of the high level place to start. And then as the collaboration continues, I would say that there is a sense in which you really kind of drill down and you learn some more machine learning and they learn some more physics, and you need a little bit of that on sort of both sides really to make progress. You can't just kind of hand them off a math problem and say go, but I think you can kind of start with a very abstract sort of view and slowly build upon that.
Thank you. Yeah, that is, you know, the way forward, seeking these partnerships and then sharing expertise. And that's really the recipe for success.
Yeah,
so,
I agree.
Thank you very much for the talk, Bryan. It was very exciting. It is great to see the breadth and depth of applications of AI across campus, and what is happening in the physics department is really exciting.
Yeah, thanks. I'm happy to have given one.
For next week, we are going to have a speaker from NVIDIA. She's going to tell us about how they are advancing the construction of software and AI applications for predictions. So invite your friends, your colleagues, spread the word about these seminars. It is really a way to create synergies to make students aware about research opportunities. So looking forward to seeing you all around here next week. Have a good week, everyone.